All right, welcome to Étale cohomology on November 19th, 2020. So we're currently in the process of proving the Riemann hypothesis for smooth proper varieties over finite fields. Let me remind you where we are. So last time we did some preliminary reduction. So we kind of discussed Frobenii. We discussed Frobenii and kind of precisified the statement of the theorem we're trying to prove. We did some preliminary reductions. So in particular, the main thing we did is we reduced the statement we were trying to prove, which was about the eigenvalues of Frobenius in the cohomology of any smooth proper variety, to the case of an even dimensional variety and only middle degree cohomology, and only proving an inequality for the absolute values of eigenvalues of Frobenius rather than an equality. And then we started discussing a sort of more general version of the Lefschetz trace formula, which we'll need for the proof. So there were three sort of issues we had to overcome when understanding this Lefschetz formula. So one was the case of non-proper varieties. So I indicated why the sort of general Lefschetz fixed point formula could have problems for non-proper varieties, and then explained how to salvage it for the specific case of Frobenius, or more generally for endomorphisms of a variety which extend to a compactification and where the multiplicities of fixed points on the complement kind of don't depend on whether you compute them on your variety or on the complement. And then I started discussing the case of non-constant sheaves. So for example, local systems. So that's where we were that's what we were in the middle of last time. And then there was a third issue that we had to address was sheaves over torsion rings. So over, for example, Z mod L to the N Z. And the problem here was that if we want to understand traces, well, when you take cohomology with coefficients in a sheaf, which isn't a sheaf of vector spaces, so if it's a sheaf of modules over a ring like this, the cohomology groups need not be free. So we needed to understand how to make sense of traces in that case. Okay, so let me briefly remind you where we were for non-constant sheaves. Are there any questions, by the way? So I'm just going to continue kind of discussing these issues until we get to a statement of a theorem that could be true. For non-constant sheaves, let's say we have E, which is a LCC sheaf on X. Then we like then an endomorphism of X doesn't actually act on the cohomology with coefficients with coefficients in E. So what we get, I mean, this is what I've written here will be true for any sheaf, but we'll let me actually just sheaf on X Étale. So one gets by functoriality, one gets a map from HI of X Étale with coefficients in E to HI of X Étale with coefficients in phi upper star of E. Okay, and now to get something so this is not the kind of thing that you can take the trace of, right? Because the source and target are different. So in order to get something we can take the trace of, which is what we want to do if we want to have some kind of Lefschetz formula, we need a map to HI X Étale E. So we need this. Okay, and one way to get it is if we already have a map from phi E from phi star of E to E. All right, so then we can just take this to be kind of applying phi E to the coefficients. Great. So given such a map, we also get endomorphisms of the fibers of E over the fixed points of phi. So given phi E, we get a map, excuse me, sorry, we get a map from phi star E, well, the stalk of that at some point x. So this is just equal. So in general, if you take the stalk of a pullback, that's just equal to the stalk at phi of x, and phi E at x gives us a map to the stalk of E at x. So in general, we get something like this. So in particular, if x equals phi of x, so if we have an honest fixed point, we get a map, which I'll call phi E comma x from ex to itself. So which is just this composition. And okay, so here, if we have a fixed point, phi of x is equal to x. Okay, so this is where we left off last time. And then I commented, so the sort of theorem we want in this case is that if x is x naught is a variety over a finite field, and x is its base change to an algebraic closure, the sort of theorem we want is that that the sum over x in the fixed point set of phi, so here phi will actually be Frobenius, but we'll discuss that in a second, of the trace of these phi sub x's on ex should equal the sum, the alternating sum of the traces of well, what I'll call phi comma phi E star. So that was this endomorphism on hi x étale f. Okay, and sorry, this should be compactly support the cohomology. So this is the kind of thing we'll want. And indeed, something like this will be true when phi is Frobenius. So there's sorry, this f should be an E. So I want to make a couple remarks. So first of all, this thing here is arithmetic, right? This is something about taking a fixed point of, let's say, Frobenius on x, that's some arithmetic data on x, and then looking at the action of the well, we'll see in a second, the action of the Galois group of that of the residue field of that point on the fiber of ex. This thing is more geometric. So in particular, this x étale here is the base change of x to fq bar. Okay, and then at the very end of last time, I discussed there's sort of a motivating example, which one should always try to think about in the case of when you think about these Lefschetz fixed point formulas, is the case where x is a finite set. So then this theorem becomes almost tautological, but it's still worth working out. So here, the only non-vanishing thing here is where I is 0. Sorry, this R should be an I. So we only get something where I is 0. If you think a little bit, you'll see that the content of this theorem is that the only contributions to the trace are coming from fixed points, and the proof is just that the trace of a block matrix only sees the traces of the blocks on the diagonal. All right. Are there any questions about this before I move on? Okay, so there's something I haven't told you yet, which is, so we're going to apply this when phi is Frobenius, and then the question is, where does this phi sub E come from? So here's the question. So when is there a natural map? Let's call it f star. So fe from f star of E to E. Okay, and the answer is so the answer is if so here remember f was the relative Frobenius on x base change to fq bar. or on X. I'm sorry, X is already base changed to FQ bar. So the relative Frobenius on X. So the answer is if E comes from a sheaf, on X naught. So let me briefly explain why this is true. So the proof is remember, so last time we showed the following. We proved that that the absolute Frobenius is a map from the Étale side of X to the Étale side of X is naturally isomorphic to the identity map. So let me briefly recall what that means. So a map of sites is a functor going the other way. This functor is just you kind of base change along absolute Frobenius in this case. So the content of this statement is that given an Étale morphism to X, its base change along absolute Frobenius is naturally isomorphic over X to what you started with. Okay, and the proof is just that the natural isomorphism is given by relative Frobenius on that Étale morphism U to X. Okay, so what this tells you, so the corollary of this proof is that given let's say E naught on X naught, so here X naught is a scheme over FQ, there's a canonical isomorphism between the pullback of E naught and E naught. Well, why is that true? It's just because this functor, sorry, this functor here is naturally isomorphic to the identity functor, and that natural isomorphism is this isomorphism. Okay, and then restricting to X Étale gives the desired Fe. Okay, so that's the proof. So we now actually have what we needed here to make sense of a statement like this. We have this phi sub E. All right. Are there any questions about this? So let me maybe I can make this slightly more explicit. So let's make this slightly more explicit. So we've constructed a natural isomorphism F inverse of U to U. Sorry, F inverse of U to U. So applying E to this. So taking sections on E, we get a E F absolute inverse of U to E of U. So this is exactly the same as a map from the push forward of E to E, right? Like these are sections on the push forward and these are sections of the sheaf itself, and then a junction between push forward and pull back gives a map. So this map is actually an isomorphism, and then a junction gives a map like this. Okay. So that's a sort of more explicit point of view. Okay, so let me just state the target theorem then. So the target theorem is going to be the following. So if U naught is a smooth curve over FQ, and then E naught is a locally constant QL sheaf on U naught, then the following statement is true. So this is just what I wrote before, except with phi replaced by this relative Frobenius. So X in U fixed by relative Frobenius of the trace of Fx on Ex So we now have these maps from this discussion. So this sum of traces should be equal to the alternating sum of the trace of f on the compactly supported cohomology of U with coefficients in E. Okay, and here the notation as usual is that U is the base change of U naught to F Q bar, and E naught is the restriction of E to U. All right, so are there any questions about this target theorem?
You mean curve here or variety?
So we're only going to use it for curves, in fact, but yeah, it'll be true for arbitrary varieties. So, but this is I mean, the reason I've stated it this way is that I'm going to, well, hopefully later on, I'm going to sketch the proof, and we'll reduce it to the case of smooth proper curves, where we already know a related statement for constant sheaves. Are there any other questions?
How did we solve the problem with the multiplicity?
Yeah, so that was just by restricting to only considering Frobenius. So the issue that happened was that maybe if you take the compactification of U, and maybe if you compute the multiplicity of a fixed point on the complement, that you would get a different number than if you computed the multiplicity on the compactification. And that doesn't happen for Frobenius because the multiplicity of fixed points of Frobenius is always 1.
Yeah, I remember. Thanks.
Great. Yeah, that's a good question. Any other questions before we continue? Okay, so with this in hand, we can make a definition. So this is the definition of the zeta function of a sheaf. So here's the situation. So U naught and E naught will be as above. So U naught will be a smooth curve and E naught will be a locally constant QL sheaf on U naught. All these definitions make sense again without U naught being a curve. Then we're going to define the zeta function of U naught, E naught, and okay, it's in the variable t. And what it is it's a sort of natural generalization of the zeta function in the Weil conjectures. The idea is just that we're going to replace point counting with kind of this quantity. So this quantity just counts points if E is the constant sheaf QL. So what do we say? We make the definition that this is going to be the exp of the sum over M of the sum over x in U f to the M. So here, these are the fixed points of the mth power of Frobenius, or in other words, the fq to the m rational points of U naught of the following quantity. So we take the trace of fx to the m, sorry, let's say fx. Well, let me write it this way, fxm. So what this means is it's the q to the m Frobenius on ex, and then times t to the m over m. Okay, and the main point of this definition is that the target theorem implies that this zeta of U naught E naught t is always rational. And this is just by the same argument that that the zeta functions of varieties were rational. One can replace this exponential with more or less the characteristic polynomial of Frobenius acting on the cohomology of these sheaves, which we know are finite rank QL vector spaces and only they only are non-vanishing in finitely many degrees. So this target theorem, well, plus the finiteness theorems we know. So finiteness theorems for Étale cohomology imply the rationality of this zeta function. So maybe a couple examples. So I already mentioned this one. So the first example of E naught is just QL, then zeta of U naught QL T. So this is like the constant QL sheaf QL is just the usual zeta function of U naught. But another example, and maybe this explains why we care about this definition, is so suppose we have X naught to U naught is a smooth proper morphism. Then you can take let's say E naught I to be the push forwards, so the derived push forwards. Maybe I'll call the morphism pi. So the right derived push forwards of the constant sheaf QL through pi. And then you can get a zeta function, zeta naught, let's call it zeta I of, well, let me just use the notation we already have. So zeta of U naught EI naught T. So basically the point is that the alternating product of these things, so product of this to the -1 to the I, is the zeta function of X naught. Sorry, I'm mixing my notation up here. I think I'm using sub X naught. So this just follows by the Leray spectral sequence. For pi. So this isn't totally obvious. So the content here is that, well, there's a spectral sequence computing the cohomology of X naught in terms of the cohomology of these sheaves. The point is that if you only care about characteristic polynomials of Frobenius, the differentials won't matter, since the differentials are Frobenius equivariant. Anything that gets killed by the differentials in that special sequence will already cancel out when you take this alternating product. So somehow the zeta function of what you get at the E2 page of the spectral sequence is the same as the zeta function at the E infinity page. All right. Are there any questions about this?
Actually, I'm curious about this I. Is it infinitely a product, or?
No. This is so these are here. This is a smooth proper morphism. So for example, by proper base change, we know that that these RIs vanish in large degree.
Okay, I see.
And then we're done. Yeah.
Right.
Yeah. So here we used smooth and proper. Well, okay. So derived push forwards always vanish in high degree. Which isn't obvious, but we use smooth and proper to say that these things are actually locally constant, or at least QL sheaves. But strictly speaking, we don't actually need that for the definition of this function. Great. Okay, so I want to make a couple remarks. So remark one is that we wrote this target theorem, so this sort of more general version of the Lefschetz trace formula, in terms of compactly supported cohomology, but just using Poincare duality. We could have written it in terms of just H2 minus I of X with coefficients in E of 1, sorry, E dual of 1. Okay, so that's one comment. So there's if you just if you dualize your sheaf and twist by the cyclotomic character that comes from Poincare duality, then you can just replace these compactly supported cohomology sheaves with just, sorry, compactly supported cohomology with just usual Étale cohomology. And then two is so from this point of view, this formula is kind of completely group theoretic. So this formula is actually, it can be reinterpreted in terms of pi1. Okay, and this, so Bob asked why we were talking only about curves, and so this is only true for curves. So let me briefly explain that. So let's remind ourselves. So there's a correspondence between least QL sheaves on U naught and well, we're given a base point, pi1 U naught, let's call it U. So this is the Étale fundamental group representations into let's say G. So given a least QL naught sheaf E, we get a representation into the fiber of E, or the stalk of E, sorry, at our base point U. And these representations are continuous. Great. So the what I want to explain is briefly how to interpret this formula that we wrote up here, how to interpret both of these sides in a purely representation theoretic way. Okay, so let me remind you, so the left-hand side was the sum over x in U naught, so fixed by Frobenius, or let's say U fixed by Frobenius. So that's the same as U naught of FQ of the trace of the Frobenius at x on the fiber of E at x. All right, so these points of x, I claim that they give you kind of a canonical conjugacy class of elements in this pi1 rep. So given an element x in U naught of FQ, we get a map. So this is the same as a map from spec FQ to U naught, right? That's just what a rational point is. And given this data, we get a map, we get a map on pi1s. So we get a map from the pi1 of spec FQ, which is just the absolute Galois group of FQ, to the Étale pi1 of U naught. Well, not with base point U, but with base point kind of a geometric point lying over x bar. So where does this geometric point come from? Well, when you pick an algebraic closure of FQ in order to define this Galois group here, you've picked an embedding of FQ into FQ bar, which is the same as a map from spec FQ bar to spec FQ, and then that maps into U naught. Okay, this group and this group though are isomorphic to each other. And they're isomorphic in a way which is well defined up to interconjugacy. So just like when you take fundamental groups of connected spaces, if you choose two different base points, you get the same group, and it's the same in the sense that there's an isomorphism given by choosing a path. And if you choose two different paths, then the isomorphisms you get differ by conjugating by a loop. Okay, so what this means is that you can take the Frobenius element fx in here and map it over here, and here this kind of class of Frobenius in pi1 Étale of U naught x bar. So you get a well-defined element here, and then when you choose an isomorphism to pi1 Étale U naught with our base point U, you only get something that's well-defined up to conjugacy. Okay, but we're only taking traces. So traces here only detect conjugacy, right? So the point is now here we can interpret this. So we can interpret this as a trace of our Frobenius element fx inside of pi1 Étale of U naught. Okay, so we've now given a group theoretic interpretation of this left-hand side. Are there any questions about that? So I gave you, we have a representation of this group, we have a conjugacy class of element in this group, and then we can take its trace. Okay, so let's look at the right-hand side. So let me remind you, so this had pieces that looked like trace of the Frobenius on HI compactly supported cohomology of U here with E coefficients. And then here we're going to have to use Poincare duality. So this is the trace of F inverse. So this object is dual to the normal cohomology on U of E dual boosted by 1. So we can get rid of that dual at the cost of replacing F with F inverse here, right? The trace of a dual matrix is the inverse of is the trace of the inverse matrix. All right. So here this I claim is also a group theoretic invariant in the case of a curve, as long as the curve is not P1. So now if as long as U is not, let's say as long as U is affine, then my claim is that this action on H2 minus I of U with coefficients in E dual of 1 can be interpreted group theoretically. Okay, and why is this? It's because curves, because U, so another way of saying this is that H2 minus I of U with coefficients in dual of 1 is isomorphic to H2 minus I of the Étale fundamental group of U with base point U here with coefficients. So this is continuous group cohomology with coefficients in the fiber of E dual of 1 at U. Okay, so why is this? So this is just the fact that affine curves are Étale pi 1s. And we've discussed this. I mean, this is like the definition of that fact. So we discussed this when we discussed pi 1s. When we discussed pi 1, the content was that this is true for any variety which has cohomology vanishing above degree 1. And we checked that was true for affine curves. Are there any questions about this? So another way of saying this is that the cohomology of the finite Étale site is this thing on the right hand side is the cohomology of the finite Étale site almost by definition, and the claim is that cohomology is the same as the cohomology of the Étale site, which is what this site is. All right, so there's one last thing we have to interpret, which is this action of F inverse, and let me just briefly describe that. So how to interpret that group theoretically? So the action of F, or F inverse, can be described group theoretically as follows. So we have our map from U0 to spec FQ, and this induces a map from the Étale fundamental group of U0 with base point U to the absolute Galois group of FQ bar over FQ. Okay, and it's a theorem which I mentioned and said a word about the proof about, but I haven't given you details, that the kernel of this map is pi 1 of U with base point U little u. So this is the kernel of this map. So if you have a short exact sequence of groups, the last group inherits an outer action on the first group just by conjugation. And the claim, which I won't prove, but it's a matter of unwinding definitions, is that the outer action of the absolute Galois group on the Étale fundamental group of U, well, first of all, induces an action on cohomology, So this is, maybe let me put the E dual of 1 here. So this is formal. So the automorphism group of this group acts on cohomology just by functoriality, and an inner automorphism acts trivially. So we get outer automorphisms give us actions, and moreover, this action agrees with the sort of geometrically described action, with the geometrically described Frobenius action. So this is also a matter of unwinding definitions. So the actual input is this discussion of Frobenii from last time, namely that the relative Frobenius acts as an inverse to sort of the arithmetically defined Frobenius. Okay. Are there any questions about this? Okay, so let's scroll back up to our target theorem and maybe I'll copy and paste it and move it down. Oops. So here is our target theorem. So we're going to start discussing what we need to prove it, and we'll see we immediately run into a problem. So the idea is as follows. So we want to. So the idea is step 1 is we first want a formulation for torsion sheaves, for LCC torsion sheaves. Then we'll try to pass to a cover to reduce to the case of constant sheaves. So here E was a QL sheaf, and then we kind of pass to the inverse limit. To give the statement for QL sheaves. So the problem is in step 1. So the formulation for locally constant torsion sheaves is not clear what it should be. And the reason why is exactly what I mentioned before. There's no reason that these groups should be free, and in general they won't be free. And so it's problematic to actually define what a trace is. Okay, are there any questions about this? Okay, so let me kind of state the target theorem prime, and then we'll make sense of what it means. So target theorem prime is the following. So U naught will be a smooth, geometrically connected curve over FQ. E naught will be a LCC sheaf of flat Z mod L to the n Z modules, where here L is not equal to the characteristic of FQ. Then the statement we'll want to prove is that the same thing as before, basically. So the sum over the fixed points of relative Frobenius in U of the trace of Frobenius on E naught X, well, EX, is equal to the alternating sum of the compactly supported cohomology of the traces of Frobenius on the compactly supported cohomology of U with coefficients in E. Okay, and here I'm using the same notation as before. So U is the base change of U naught to the algebraic closure, and E is the restriction of E naught to U. Okay, so the question that we have to address now is, what does this mean? yeah, so in particular, we have to figure out what this means if these groups are not free Z-mod L to the n Z modules. And we won't actually do that. What we'll make sense of is what this alternating sum means. Okay. So we need the following definition. So this is the definition of a perfect complex. And I'm going to restrict to the case where R is a Noetherian local ring. There are slight issues with dropping. Well, I mean, there's not really any issue with dropping locality. I mean, there's a perfectly good definition for general Noetherian rings. It's a little complicated, which is why I'm restricting to this case. And Noetherianity also causes some mild issues. But I mean, this is something this is a topic that's very well understood. But I'm going to kind of discuss it in a special case, which will be enough for us. So the definition is a complex of R modules is perfect if it is, let's say, quasi-isomorphic to a complex, a bounded complex, sorry, of finitely generated free R modules. Okay, so in general, without this local condition, you would ask that it be locally quasi-isomorphic to such a thing. But I don't want to get into what exactly that means. Okay, so what's the point of this definition? So the point of this definition is that we're going to show that the complex computing these groups is perfect. It's quasi-isomorphic to a bounded complex of finitely generated free R modules. That complex will have a not quite well-defined endomorphism, and then we'll be able to take the sum of the alternating sum of the traces of that endomorphism on this complex because it's a bounded complex of finitely generated free modules where traces make sense. Are there any questions about the kind of strategy here? Okay, so let me kind of explain the main sort of homological algebra proposition that tells us that traces make sense. So as before, R is a Noetherian local ring. When I say ring, by the way, I always mean the commutative ring, in case that wasn't clear. So suppose M is a perfect complex of, well, let me say it this way. So suppose M is a complex of R modules and gamma from P to M is a quasi-isomorphism with P a bounded complex of finitely generated free R modules. So this is another way of saying M is perfect. So strictly speaking, being quasi-isomorphic to a complex with some property doesn't mean that there's a map one way or another. It means that there's a zigzag of maps. You can always take that zigzag to be a hat. And here I've assumed there's an honest map from a perfect complex, which we won't really need, but I mean, one can always reduce to thinking about this case. Now suppose M has an automorphism. So suppose alpha from M to M is an endomorphism. Then the theorem is that there exists a beta from P to P such that the following holds. So first of all, the diagram beta from P to P M here to M, this is alpha, these are maps for gamma, commutes, beta is well defined up to homotopy. So this is like homotopy of maps of complexes. And the key is that the trace of beta on P, which is by definition the alternating sum of the traces of beta on PI, or sorry, PR, is independent of all choices. So all choices here means not just the choice of beta here, but also this gamma here. So also the choice of perfect complex quasi-isomorphic to M. So this is not, I mean, this is pure homological algebra. It's not trivial homological algebra. You really have to prove it. And this more general, I mean, there's like, this is part of a whole kind of package of, in my view, quite interesting and non-trivial results. So for example, another thing you can do is you can ask to try to take the determinant of a complex. So that would be like, if you have a perfect complex, you could take the alternating tensor product of the top exterior powers of the objects here. And that, it turns out, is also kind of canonically independent of the choice of perfect complex quasi-isomorphic to your given complex. But proving that is like in Mumford-Sibylian varieties, it's like a 10-page proof or something. It's like fairly involved homological algebra to do all the details. Are there any questions about this statement? Okay, so I'm not going to prove it. So the proof is non-trivial homological algebra. And when I say non-trivial, I mean like you'll be able to do it if you sit down and try it. But I just don't want to claim that it's easy. But let me just maybe briefly remark on like what the point is. So the reason something like this should be plausible is that suppose you have so sort of the moral reason it's true is suppose you have a short exact sequence, so 0 to A to B to C to 0, and an endomorphism of it, so a commutative diagram like this. And let me call these maps beta. So then the statement is that the trace of beta on A plus the trace of beta on C equals the trace of beta on B. So this is if this is if here these A, B, and C are free R modules, finitely generated free R modules. Okay, and I mean the proof is it's not hard. You just pick a splitting that will write beta in kind of block upper triangular form, and then you'll see that the trace in the middle is just the trace of the two blocks. All right. Are there any questions about this? Okay, so the big remark so this doesn't just solve our problems. So this tells us how to define the trace of an endomorphism of a complex if that complex is perfect. So if it's quasi-isomorphic to a bounded complex of finitely generated free R modules. So the remark is that not all complexes are perfect. So not all complexes are perfect. So can anyone give me an example of a complex which is not I mean, it's very easy to give examples of complexes that are perfect. So you just take a complex of finitely generated free R modules where R is your ring. So can anyone give me an example of a complex which is not perfect? So not all complexes are. Yeah. So Jingwon says non-smooth stuff. Jose says not. Yeah. So you have to. So here, let's just say R is let's just say R is Z mod L to the NZ for n bigger than 1, and I want to. Yeah. So Jingwon says, yeah, there is some relationship to. So if you take coherent cohomology on smooth varieties, there's some relationship to that being computed by a perfect complex. But yeah, so I wanted like an honest example. So give me a Noetherian local ring. So let's say Z mod 4Z and a complex of modules over it, which is not quasi-isomorphic to a bounded complex of finitely generated free modules.
Can we take something concentrated in degree 0 that the single module doesn't have finite projective dimension?
Yeah, that's great. So can you give me an example?
Oh, geez.
Yeah, that's a very good idea. So right. So having finite projective dimension, right? So if you have a module, so yeah, so Sasha's idea is good. So let's just look for an example where M is concentrated in degree 0. So it's just an R module. So being quasi-isomorphic to a perfect complex implies it has finite projective dimension, because a perfect complex is a finite complex of projectives. So how would you test if a complex has finite projective dimension? There's a sort of homological algebra test for this.
Just take the H0 and see what the dimension of that thing is.
Sorry, H0 of what?
Of the complex.
What does it mean to take H0
sorry,
of a complex?
Let's see. Let's think harder about this.
Yeah, so my hint is that maybe it has something to do with tors. Yeah, so let me give you an example. So let's take Z mod LZ as a Z mod L squared Z module. Okay, so my claim, so here we can view this as a complex concentrated in degree 0. So the claim is that the complex of Z mod L squared Z modules, which is just Z mod LZ in degree 0, is not perfect. So it's not quasi-isomorphic to a bounded complex of finitely generated free modules. Okay, so the proof is as follows. So suppose it was. So suppose it was. So suppose there's some quasi-isomorphism. P. Well, there's a priori chain, but for simplicity, let me just assume it goes like this. So this is a projective resolution, right? So this would imply that just by the finiteness of this P, that tor I Z mod L squared Z of Z mod L Z against stuff would vanish for I outside of some bounded range. So for I large. But I claim that doesn't happen. So can anyone help me compute the tors of Z mod LZ as a Z mod L squared Z module? So how do you compute tors? You need a projective resolution, right? So let's start making a projective resolution. So there's this rejection from Z mod L squared Z to Z mod LZ. Can anyone help me keep resolving this? Yeah, so all terms, exactly right. So you can just take all terms Z mod L squared with the differential multiplication by L. Okay, and then so on. Okay, so this implies, for example, that tor I of, sorry, I'm putting the indexing in the wrong place. So tor I over Z mod L squared Z of Z mod L against Z mod L is just equal to Z mod L for all I. So why is that? Well, how do you compute that? You tensor this complex with Z mod L and then take the cohomology. But when you tensor with Z mod L, all these differentials just become 0. So you get the complex which is 0 differential in every degree, and every term is Z mod L. So its homology is Z mod L in every degree. Okay, so this implies, so this is a contradiction. So this implies that the Z mod L squared Z complex, Z mod L, is not a perfect complex. Are there any questions about that? Okay, so nonetheless, there's a homological criterion. So there's a homological criterion for when a complex is perfect. Yeah, so maybe let me remark, I mean, already, so a priori, that there's some problem here. So that tells us these groups themselves will not in general be perfect complexes. It's not hard to make examples of sheaves here where the cohomology groups will have infinite Tor dimension, or will not have finite projective dimension as Z module to the n Z modules. So that tells us we can't actually work with these groups individually when we want to make sense of this side. So nonetheless, there's a criterion for when a complex is perfect. For when a complex.
Quick question for these complexes concentrated in degree 0. So certainly not having finite projective dimension like this is necessary, but is it sufficient?
Yeah, so we're about to see the criteria.
Great,
I'll tell you the answer to that. Yeah. So the proposition is as follows, and I think this is maybe due to Mumford. It is as follows. So R is a Noetherian local ring as before. And suppose that M is a complex of R modules. So then there's two steps. So the first step is just to find a kind of free resolution. So a free resolution we can find. So we want to find a free resolution which is bounded in one direction, and that's pretty easy. So if HR, so if the cohomology of this complex M is finitely generated for all R, and HR of M equals 0 for R very big, then let's actually give it a name. So let's for R bigger than some M. Then there exists a complex Q mapping to M, which is a quasi-isomorphism. So with each of these QIs finitely generated and free, and such that that QR is actually just equal to 0 for R bigger than M. Okay, and the proof is not very hard. So of this statement, I mean, I won't write anything down, but I'll say the idea. So first of all, you can truncate M to make it just a complex with the same cohomology, supported in degrees less than or equal to M. Sorry. So there's this. So you just replace the last term of M with like the kernel of the differential D in order to do that, and then you just pick a free module surjecting onto that. It's possible to do that with a finitely generated free module by the finite generation here. Okay, and then you start just making finitely generated free modules mapping in. I mean, it's very easy to map out of a free module. So all you have to do is make sure you're hitting all the cohomology, and then you kind of win. All right. So this statement is pretty easy. Okay, and then if in addition, so now we have this Q. So HR of Q tensored over N equal tensored here. Here, this N is going to be an arbitrary R module. I'll write that down in a second. So if this is 0 for R less than 0, and all finitely generated R modules N, then the statement is that there exists a quasi-isomorphism Q to P with P a complex of finally generated free modules supported in degrees 0 to m. Great, so that's the statement. Are there any questions about the statement? So part one says that if we have some cohomological vanishing in high degree and the cohomology is finitely generated, then we can almost get a perfect complex. So we can get a perfect complex quasi-isomorphic to our given one, except that it might be supported infinitely far to the left. So it might be supported in not be supported in finitely many degrees. It might not be a bounded complex. And then here with this condition here, so this condition here is called is a condition on Tor dimension. So it's this condition. So this condition has a name. It's called being of Tor amplitude 0m. So if you satisfy this condition, then one can actually find a perfect complex. So this is the answer to your question, Sasha. Okay, and then you might ask, well, what if you replace this 0 with another number? Like what if you have vanishing in degree like -1 billion? Well, it's not a problem. You can just shift the complex to the right to make it a 0. Yeah. So in general, the general statement would be if you have Tor amplitude less than 100,000, less than -100. If this is 0 for r less than -100,000, then you'd get a complex supported in -100,000 to m. Okay, but that's just an immediate corollary of this by shifting. So the proof. Let me just say a word about the proof of the second bullet point. So it's actually pretty easy. So you just you just replace Q naught with Q naught modulo the image of Q minus 1, so like D of Q minus 1, and then you have to, what do you have to do? You have to check its flat. So a finitely generated flat module over a local ring is free, or sorry, over a Noetherian local ring is free. Maybe that's actually true of arbitrary local rings. I have to think about it for a second. And okay, how do you check this flatness? Well, it more or less follows immediately from this Tor vanishing here. All right, so that's the proof idea. Okay, so are there any questions about this criterion? All right, so now here's our observation. So the observation is that this is satisfied for the cohomology computing this is satisfied by the complex computing the cohomology of our nice like flat Z mod L to the n Z sheaf. So let me make a, yeah, let me write this down. So the point is that the projection formula plus the finiteness theorems we already know imply that for E and a flat LCC Z mod L to the NZ sheaf, the complex R gamma, I'll remind you what this means in a second, U Étale E satisfies the conditions of the theorem. Okay, so here projection formula is used to check this condition. And then the finiteness theorem tells you that the cohomologies are finitely generated. Okay, so let me just remind you what this is. So what this is you choose a injective resolution of your sheaf E, then you take the global sections of that, and that's a complex whose cohomology computes the sheaf cohomology of E. Okay, so the theorem implies that this complex is quasi-isomorphic. So this implies that this complex R gamma U Étale E is quasi-isomorphic to a perfect complex, or is a perfect complex, sorry. So it's quasi-isomorphic to a bounded complex of locally free. It is perfect. So, okay, and then the corollary of this is that this expression, sum of -1 to the R of the trace of Frobenius on, well, I wrote it as HIC of UE. Well, this is going to be, we can reinterpret this using Poincare duality or Verdier duality, but let me just erase this compactly supported to avoid stating that. So at least this trace, I put it in quotes, this alternating sum makes sense by the previous proposition because we can compute it on a perfect complex. Because we can compute it. On a quasi-isomorphic complex, which is bounded and consists of finitely generated free modules. So I guess actually I could just put a compactly supported here. I mean, if you put compactly supported here, what you have to check to apply this is that J lower shriek of E still satisfies the conditions of the theorem, but that's still a complex. That's still a complex of flat Z mod L to the N Z modules. It's no longer LCC, so one has to think for a second, but it's still fine. All right, are there any? Or you could use Poincare duality, but you have to think a little bit about it because it's in the torsion setting. So are there any questions about this? Okay, so I'm not going to, so we've now gotten to the point where we understand both sides of this equality. So this was the sort of the non-trivial part to understand. I'm not going to give the proof. If we have time at the end, I'll give the proof. But it is more or less, I mean, I kind of said what the idea was. So the idea was this. So more or less, you reduce to the case of constant sheaves by passing to a cover. And then, okay, then you have to prove something for constant sheaves, and that thing is not trivial, but it's closely related to what we already did. So I'm not going to do that now because we're running low on time, and I want to get to the geometric content of the Weil conjectures. So let me start, and we only have 6 minutes left today, unfortunately, but let me briefly start introducing sort of the main. So this is now the introduction to kind of the main geometric ideas. Okay, so the idea will actually be to reduce to statements about certain sheaves on open subsets of P1. So how does one reduce to such a thing? So given X, let's say, which is a projective variety, so let's say so inside of Pn, so some smooth projective variety. We're going to choose a Lefschetz pencil, and I'll discuss these more next time. But loosely speaking, what we'll do is we'll find a map from the blow up of X at some locus to P1 with good properties. So first of all, with such that the fibers only have very mild singularities. And such that the monodromy, and I'll explain what that means, on the middle cohomology, the fibers has large image. So let's suppose this map is pi, and this has fiber dimension, well, the dimension of x minus 1, so fiber dimension d, say. So what we'll try to understand is we'll try to understand RD pi lower star of QL. So this will be a this will be here U inside of P1 will be some open subset, and then we'll restrict to the more locus x0. So this is the locus where pi is smooth. So let me call this pi smooth. So here we're going to be taking the cohomology of the smooth fibers. So this will be a sheaf. This is a QL sheaf on U. And what we'll do is we'll axiomatize the properties of such sheaves and study sheaves on P1 with this property. So the idea will be to list all the properties, the good properties of this sheaf. So let me call it E. And then analyze the consequences for the cohomology H1 of U. This is the only interesting cohomology with coefficients in E. All right. So I mean, this idea is you still have to do a lot of work once you have this idea, but the point is that this will allow one to do some kind of induction on dimension. So here, suppose we understand something about the dimensions of the fiber. So this will tell us something about the fibers of this sheaf. And then hopefully we can use that to understand this object, which goes into computing the cohomology of x0 and hence the cohomology of the blowup of x. So using Leray special sequence. So this will allow us to do some kind of induction on dimension. So next time, I'm out of time, but next time I'm going to kind of state the main theorem that we'll need about sheaves of this form, and then how we're going to use it, and then we'll start proving things. All right. Are there any questions about that? If not, then I'm going to stop recording, and I'll see you on Tuesday. And there will be no class next Thursday because it's Thanksgiving. But thank you all for coming as usual. And I'll stick around for a couple minutes in case there are any questions.